Hi students, welcome back. Today we are going to look at phase equilibrium. Basically, phase equilibrium is about the mixing of two liquids. First, let us look at liquid mixtures. There are three types of liquid mixtures, which are miscible liquids, miscible liquids, and partially miscible liquids. Miscible liquids consist of two different liquids. They form a homogeneous solution when mixed in any proportion. For example, we have methylbenzene and benzene, ethanol and water, ether and benzene. Next, we have immiscible liquids. It is formed when two different liquids form two layers when mixed. Denser liquid will be at the bottom, while the less dense liquid is at the top. For example, we have CCl4 and water, benzene and water. Last one, we have partially miscible liquids. When a very small amount of liquid is mixed with a large amount and a homogeneous liquid is obtained. For example, we have ether and water. Molecular explanation. Miscible liquids have molecules that can form bonds with each other. As for immiscible liquids, there are no forces of attraction between the molecules of liquids. For partially miscible liquids, the upper layer consists of a saturated solution of water in ether, and the lower layer consists of a saturated solution of ether in water. Vapor pressure is not constant in miscible liquids at a given temperature, but varies with the proportion of two liquids. As for immiscible liquids, have individual vapor pressure. For the partially miscible liquids, it is not related. Okay, mixtures of liquids. So let's look at the definition again. Okay, for two miscible liquids, two liquids are said to be miscible when they dissolve completely in each other in all proportion to give a homogeneous solution. So they have very similar in the structures. Okay, so the example is ethanol and water. Okay, so ethanol has hydrogen bond between the molecules. Water also forms hydrogen bonds between the molecules. So both of them can form hydrogen bond with each other. As for the immiscible liquids, example is benzene and water. Okay, so these two cannot form bonds with each other, so they will form two layers. Okay, upper layer is the benzene, then the lower layer is the bottom layer is the water. We can separate the liquids using the separating partner. Okay, so you look at the structure of immiscible liquids. Another example is hexane and water. So both of them cannot mix with each other. So let's look at the structure of hexane, the forces between the molecules. So it's van der Waals forces okay, between hexane molecules. So London forces is induced dipole-dipole forces. As for the water, it's a hydrogen bond between the molecules. Okay, so they cannot mix with each other. Now we look at ideal solutions. In an ideal solutions, they contains two components A and B. The intermolecular forces of attraction between A and A, between B and B, and lastly between the mixtures A and B are equal. Okay, so the forces are all equal. When ideal solution is formed, there is no change in volume on mixing. There is also no enthalpy change on mixing. Heat is neither liberated nor absorbed during mixing. Okay, so you can look at the pictures. Okay, because they form bond with each other, so it takes the same amount of energy for the solvent molecules to break away from the surface in either case. Okay, so the forces are the same between the pure one, pure A, pure B, and the mixtures. Okay, so most solutions deviate considerably from the ideal behavior because intermolecular attraction between the components in the solution are different from the intermolecular attraction between the pure components. Means the forces between the pure A and pure B and the mixtures A and B are different. Okay. Forces are different. Okay. Next we look at RAOULT'S law. RAOULT'S law states that the partial vapor pressure of A in the solution at given temperature is equal to the vapor pressure of pure A at the same temperature multiplied by the mole fraction of A in the solution. So in exam you can just write formula where the PA equal to XA times PA. Okay. So the PA stands for partial pressure of A in the ideal solution. XA is the mole fraction of A, and PA0 is the vapor pressure of pure A. Similarly, for liquid B, is PB equal to SB multiplied by QB. Okay, so you have XA plus SB equal to 1. Okay. So for revision, let's look at what is vapor pressure. Vapor pressure is formed when there is a lid on the container. The gas phase molecules are trapped, so they are a vapor. The vapor creates a pressure. So the lid blocks the escaping vapor. Molecules in vapor phase collide with walls and cause a pressure. That is the vapor pressure. The rate of evaporation equal to the rate of condensation. So the temperature change, rate of evaporation change, vapor pressure also change. Okay, so the vapor pressure is depending on the temperature. Okay, as for boiling point is of the substance is formed when the vapor pressure of the liquid is equal to the atmospheric pressure. So we need to know these two terms because we need to draw the graph. Graph of vapor pressure against the mole fraction and the boiling point composition diagonal. Okay, let's look at the vapor pressure composition diagram for an ideal solution of hexane and heptane at constant temperature. So the y-axis is the vapor pressure, the x-axis is the mole fraction of A. So we need to draw three lines. The first line is the red color line, which is the total pressure of the two liquids. And the second line is the blue color lines, which is the vapor pressure of the liquid A. Okay. Then the second line is the vapor pressure of B. Okay, so at this point we have 100% of A. Okay. So at the y-axis, this pressure is the vapor pressure of pure A. Okay. And as for these parts, we have 100% of B. So this is the vapor pressure of pure B. Let's look at the question. When mole fraction of A equal to 0.7, from the graph you can get the partial pressure of A value equal to 5.956 kPa, 6.0 kPa, or you can use formula. Okay, PA equal to mole fraction of A multiplied by vapor pressure of pure A. So 0.7 times 8.5. Okay, so you will get 5.95. So follow the smallest significant figures of the pressure is 2. So answer will be 6.0 kPa. Okay, as for PV, the same formula. PV equal to 0.3 times 6.0. 0.3 is get from the XP, the mole fraction formula. XP equal to 1 minus XA. Okay, so you get 0.3. Okay, multiplied by the vapor pressure of pure B. So you get 1.8 kPa. Okay, finally the total vapor pressure of the solution PT, you will get PA plus PB. Okay, so 7.8 kPa. Okay, use value haven't round to add together. You also can get the value of total pressure from the graph. Okay. So total pressure will be here. Okay, so 7.8. So here is the pressure for A, partial pressure for A, the blue lines, then here is the orange line for the partial pressure of B at this mole fraction. Okay, so a solution that obeys RAOULT'S law is known as ideal solution. Next we look at fractional distillation of an ideal solution. Okay, this diagram shows the apparatus for the fractionating distillation of the liquid mixtures. Okay, the liquid mixtures will undergo repeating vaporization and condensation through the fractionating column. Okay. So here has large surface area for the repeating vaporization and condensation process. Okay, and the distillate will come out, okay, from the condenser here, condensation of the vapor here. Now let's look at boiling point composition diagram for the mixtures. Okay, for the y-axis we have boiling point, and the x-axis is a mole fraction of A. Okay, then there are two curves on the graph. The first curve is the boiling point of vapor, and the second curve is the boiling point of liquid according to the composition. Okay, so if you roll this graph, you change the y-axis to vapor pressure. So it means you roll the vapor pressure composition diagram. The vapor will be at the bottom, and the liquid will be at the top. Okay, so at this point we have 100% A. So this point is the boiling point of A, liquid A. And next we have this point with the composition is 100% of B. So we have boiling point of B here. The question asks if a liquid mixture of A and B with composition C1 is distilled, the mixture will boil at, okay, so C1, mixture will boil at T1, okay, to produce a vapor with composition of C2. The vapor with composition C2 is richer with the more volatile component. So you have to see, more volatile means lower boiling point, means it will boil easier, okay? Easier to boil, lower boiling point. So you have to look at the graph. So A is more volatile. So A is the answer. If the vapor with composition C2 is condensed, the liquid with the same composition C2 is formed. Okay, next we have example of benzene and methylbenzene. Then we need to draw the boiling point composition diagram. So given the boiling point of benzene is 80 degrees Celsius, boiling point of methylbenzene is 110 degrees Celsius. Okay, so you can draw the graph. So 100% benzene here. So boiling point of benzene 80, then boiling point of methylbenzene 110. Okay. So let's look at the question. Okay, if a mixture of benzene-methylbenzene with composition C1 is heated, the mixture will boil at T1. Okay, C1 heated. So this will liquid here. C1 liquid. Roll the line until liquid here. So the liquid boil at T1. Okay, so you roll the graph. Roll the lines to the graph of vapor, the line of vapor. Boil at T1 to produce a vapor with composition C2, which is richer in benzene, because here is more than half, so richer in benzene. If this vapor is condensed when coming into contact with the core surface of the fractionating column, okay, the condenser, the fractionating column, the liquid produced will have composition of C2. Okay, so haven't reached a condenser, so it's still in the fractionating column. Okay, so when this condensed liquid is in contact with the ascending vapor, it will boil again. Okay, so the fractionating column has many surface area for the vaporization and condensation to occur. Okay, so when this condensed liquid C2 is liquid here is in contact with the ascending vapor, it will boil again at T2, okay, to produce a vapor with composition of C3. Okay, so if the vapor is condensed, the liquid with composition C3 is produced. Okay, same composition. So by repeating the process of vaporization and condensation, the composition of the vapor produced becomes richer in more volatile component, benzene. Okay, benzene has lower boiling point. Finally, pure benzene is distilled out at 80 degrees Celsius at the boiling point of benzene. The liquid remaining in the flask becomes richer in the methylbenzene, the component with the higher boiling point. As a result, the temperature of the liquid mixture in the distillation flask rises during distillation. Finally, when the temperature reaches a boiling point of methylbenzene, it is distilled out as pure methylbenzene. That's all for the lesson today. If you like this video, please subscribe to my channel and press the notification button for the next video. Thank you.